All right, welcome. Today we're going to jump into a really fundamental skill in electromagnetism. How do you figure out the total charge that's hiding inside an object, especially when that charge is spread all unevenly? We see the effects of electric charges all around us. I mean, look at this incredible image of a dipole field. But the real question is, how much charge is actually in there creating that field? If it's not all neat and tidy, you can't just guess. You need a specific and really powerful mathematical tool.
So for this explainer, we're basing our walkthrough on a really great article over at electronicsed.com. It's called Calculation of Total Charge Enclosed Using Volume Charge Density, and it lays out the exact problem and the step-by-step thinking we're going to follow.
Okay, so here's our game plan. First, we'll set up the challenge. Then we'll grab the right tools for the job. We're going to break down the integral, crunch the numbers, and then, and this is super important, we'll talk about why this even matters. And I'll give you a checklist you can use yourself.
All right, let's get right into it. First things first. What is our mission?
Here it is. We need to find the total electric charge inside a tiny little sphere. And when I say tiny, I mean its radius goes from 0 to just 1 millimeter. But here's the catch, and it's a big one. The charge isn't uniform. That means the simple old density times volume trick, yeah, that's not going to work here. And this right here, this is the rule book. This equation tells us exactly how that charge is spread out. This is the volume charge density, ρV, and you can see it's all about r, the radius. It's an exponential function, which is just a fancy way of saying the charge is packed super tight right at the center, and then it fades out really, really fast as you move away from it.
Awesome. Mission defined. Now, before we can actually tackle this, we've got to get our toolbox ready. This prep work is absolutely key.
So, first tool in the box. What even is volume charge density? Well, the best way to think about it is like population density. A city has a packed downtown core and then these spread out, sparser suburbs. It's not the same everywhere. That's exactly what this ρV is for our sphere. It tells us, point by point, just how much charge is crammed into each tiny little bit of space. Okay, so if we want to find the total charge, Q, what do? We have to add up the charge from all those tiny, tiny points, right? Well, in math, that huge summing up job has a special name, integration. So our master formula is this. The total charge Q is the integral of that charge density ρV over the whole volume dV. This is the key to everything. Now, see that little dV in the formula? That little piece of volume? Its form totally depends on the coordinate system we pick. So let me ask you, we're dealing with a sphere? What coordinate system just feels right? What's going to make our lives the easiest? Yes, if you were thinking spherical coordinates, you nailed it. It just makes sense, right? Match the coordinates to the shape. So in the spherical system, our little chunk of volume, our dV, looks like this. I know, it seems like a mouthful, but trust me, this expression is our best friend for solving this problem. Okay, toolbox is packed. Now for the main event. We're going to put it all together into one big integral. And yeah, it's going to look a little gnarly at first, but stick with me because we're going to dismantle it piece by piece. So let's just plug everything in. We take our charge density function, we take our dV, and bam! We get this beast, a triple integral. Don't panic, it looks way worse than it is. We're integrating over the radius r and two angles, theta and phi. The trick is, we can treat them like separate little problems. And here's the beautiful part. Remember how our charge density function only cared about the radius r? That's a huge clue. It means the other parts, the angle integrals, are actually super simple. The integral for phi, going all the way around, that just becomes 2 pi. The integral for theta, from top to bottom, that just becomes 2. Easy. And just like that, we've tamed the beast. We take that 2 pi, we take that 2, and we can't forget the constant 2 that was already in our density function. Multiply them all together. 2 times 2 times 2 pi gives us 8 pi. And all of a sudden, that terrifying triple integral collapses into this. Just one single integral to solve. So much better, right?
We are so close. This is the final push to the summit. Let's knock out this last integral and get our answer. Okay, so what about this integral? Now, you could try to solve this by hand with a method called integration by parts. The source article points this out too, but it also says it's not very practical. And they're right. In the real world, you just use a tool. So that's what we're going to do. Let's use a scientific calculator or a computer program.
All right, so we plug that integral into our tool, we hit enter, and out pops this number, 1.606 times 10 to the power of negative 10. That's the value of just the integral part.
We are literally at the finish line. All we have to do now is take that number we just got and multiply it by that 8 pi we figured out earlier. And that gives us our final answer, 4.036 nanocoulombs. That's it. That is the total charge hidden inside that tiny sphere. Mission accomplished. Okay, great. So we did a bunch of math. But who cares, right? Well, it actually matters a lot. Let's zoom out and look at the big picture. See why knowing how to do this is such a powerful skill. This is not just some problem from a textbook. If you're an electrical engineer, you're using this to design things like capacitors and antennas. If you're in material science, this helps you understand and even create new materials. And for physicists, it's how you model the universe at a fundamental level. The bottom line is, in the real world, things are messy. Charges almost never spread out evenly, which makes this method absolutely essential. And to really bring this home, I wanted to give you something you can actually use. We've boiled this whole process down into a simple, reusable checklist for any time you face a problem like this.
Here it is, your 5-step plan. Step 1, look at the object. What's the shape? What are its boundaries? Step 2, pick your coordinate system. Is it a sphere, a cylinder, a box? Match the system to the shape. Step 3, write down the correct dV for that system. Step 4, plug in your unique charge density function. And step 5, the finale. Do the math. And please, please double-check your constants in your units. It'll save you so much grief.
So look at that. You now know how to find the charge in a sphere. But the really cool thing is, this isn't just about spheres. You can use this exact same checklist for a cylinder or a box or all sorts of other shapes. All you have to change are the coordinates and the limits. The fundamental skill, you've got it now. So my question to you is, what are you going to conquer next? Thanks for joining me.